So let's continue looking at some examples. Let's say I want to calculate the limit as n goes to infinity of ln of n over n. We've taken limits before with natural logs. We used L'Hopital's rule. Do you remember? We used L'Hopital's rule. So we want to do the same thing here, but remember, this is not a function, so my first step is to change it into a function. You replace n with x, and now I have a function, so I can use L'Hopital's rule because you need to take derivatives with L'Hopital's rule, so you've got to have a function. So what's the derivative of ln of x? 1 over x. What's the derivative of x? 1. So I'm really just looking at the limit as x goes to infinity of 1 over x. 0 is that limit. Okay? So because the limit, when I turned it into a function, I got 0 for the limit, that also tells me that my limit of my sequence, ln of n over n, is also 0 as well. Okay, any questions on calculating that limit? Okay, so what we want to do now, let's say I want to look at a new sequence. Let's say determine whether the sequence a sub n, which is going to be -1 to the n, is convergent or divergent. Remember that a sequence is really just a list of numbers. So I want to see what happens to this list as n gets larger. Okay, that's really what we're talking about when we're taking this limit. So remember last time I graphed these? So let's graph this. I might need a little bit more room. What do I get if I plug in n equals 1? -1 to the first, -1. And remember, these are just points because it's not a function. If I plug in 2, 1. If I plug in 3, -1, 4, 1. Do you see what's happening? You're just going up and down between, you're flip-flopping between -1 and 1. In order for this sequence to converge, this list has to eventually approach some number, right? But all it's doing is flip-flopping back and forth. So it's divergent. Because it's going to keep alternating between those two numbers forever and ever. So it's divergent. Okay. All right, let's look at another one. Any questions before I do the next one? Evaluate the limit as n goes to infinity, -1 to the n over n, if it exists. I gave you a theorem last time, so I'm going to recall that fact right here. Recall that if the limit of the absolute value of an is 0, then the limit of an is also 0 as well. And when I gave this to you on Friday, I said it's helpful whenever you have negative terms or whenever it's alternating, right? It's flip-flopping signs. So look at the one I was given in this problem, all right? If you plug n equals 1 in, what are you going to get? Is it positive or negative? It's going to be positive, right? And negative 1 to the first. It'll be negative, and then when I plug in n equals 2, it'll be positive, negative, positive. So it's going to be flip-flopping signs again. That's what I called alternating last time. So this theorem helps you whenever you have something that has negative terms or if it's alternating as well. So what I'm going to do is I'm going to take the limit with absolute values on it and see what I get. Well, if you take the absolute value of a product, which division is really just the same thing as multiplication, you take the absolute value of the numerator, absolute value of the denominator. What kind of numbers am I getting for the numerator? Negative 1 to the n. It flip-flops. What were my two values that flip-flops? Positive
1 and negative 1.
And negative 1. What do I get if I take the absolute value of those numbers? 1 in both cases. So no matter what, the numerator is always going to be 1. The absolute value of n is positive, so I can drop the absolute value now. And you can tell me what the limit is. What's the limit of 1 over n? 0, exactly. So when I had absolute values, the limit was 0, so that means without absolute values, the limit is also 0. Okay? You can use this anytime your sequence has negative numbers or if it alternates sign, positive, negative, okay? Questions? Okay. All right. Let's take another limit. Find the limit as n goes to infinity of sine of pi over n. Limits of sequences work very much like functions. That's why I said if you want to take the limit of a sequence, you turn it into a function. So we had all of our limit laws that we had for functions. We also have for sequences. I talked about that a little bit last time. But we also have properties of limits that we can use here just like we did for functions. So when you take a limit, this is a composition of two things, right? There's the sign on the outside and the pi over n on the inside. And when you had functions, as long as you had a continuous function, the limit could bypass. So this limit, I can bypass the sign and go to the inside. So it's going to do the same thing here like it did with functions. This becomes sine of the limit pi over n What's the limit of pi over n? 0, right? The numerator's fixed, the denominator gets really large, so you're going to get 0. And what's sine of 0? 0. So that's my limit right there. Okay. And this works with any kind of continuous function. So if you had natural log instead of sine, you could also bypass that. Cosine, yeah. As long as you have a continuous function, the limit can essentially bypass and just go onto the inside.